Hello，关键连 VPN pad 啊，蛮新的，好 pad
，Galaxy S9 Plus
啊，为什么不要买 Apple？这一三片，
女生说这样也是有，但是挺
等等必须说，
挺那个几十倍那个，
哦，那你买新的 pad，OK 啊，
挺快，挺这个是摔一下1500，
啊，今天我买 iPad，对，新的，喜欢 Android。
上去，也是有给的考，
没错，这个用一个人打开，
那三星那笔也是电旁边的，三星笔也是电旁边的，
对啊，大部分的都是，因为哦，它区别就是这个按键，Apple 的这个是在抓这个里面做上面的，当然我算了，因为买，但是感觉很担心啊，会倒在里面，但是其实不会，这样，
平时你做一折车没有担心过你一折一看，
这个大的结构，但是这个没有我并不清楚，
不可以，你要当心的，有人会输你的，
坐地上，这是
没有小心点就好。
之前人讲不就是那种不想坐下来是，然后他们就在你坐的时候，他们偷偷拿椅子，然后就唰，
老公，你要搞完呢？你要搞完呢？你的，
嗯，
有那个你，
我有哇，这两个是最难的，还是同一个星期，哇，给你手处理这两个，
一点都没，
都不能讲，都不能。
OK，我没有改完你们的assignment，因为我改其他课的 assignment，还有因为你们班有人也是 break 我的 assignment，所以种种原因，我还没有改完你们的 assignment。So，这样子讲啊，你们要不要一个 revision class before midterm？我们可以讨论 assignment，然后也可以讨论tutorial 全部，要么因为我欠你们东西。OK，如果要的话，你们觉得什么时间比较好？哎，可以拜六啊，如果要的话。 拜二考试嘛，对不对？拜一我不懂，拜一感觉很近的。哦，讲到可以拜六的话，如果你们要的话。啊，
讲课这么紧，
好讨论，可以讨论。你看他拜六下午拜六下午。
赖什么赖？
I prefer offline，but 如果是来什么啊，你要 online 哦也可以，但是prefer 是 offline。那5课而已 revision class for midterm to discuss the assignment, tutorial and so on. Okay 啊，下午 maybe 2 to 4 or 2 to 5, 2 to 4 depend 哦，2 to 4， 可以吗？如果你们回家，比如说燕如是回家对吗？你要 online 你就专门 online，对啊，我就做到像这样，然后你可以这样，有点像上次我们 final 这样的，呀。如果你回家 no choice 不能来 online 咯，but prefer 是大家是 offline。等我 try 去 book 那个有冷气的房间呢，这个有人家，这个有人家，但是比较漂亮的，可以吗？看我 try，if not 就是 randomly go to F4 一个。
那边的下有拍过
seriously
凤哪一间？但是是
A3 啊
但是是那时。
，OK I try 了 ，OK 了，then we fix Saturday afternoon midterm revision class. We discuss assignments and then we discuss tutorial and then yeah, discuss everything that you want to discuss. Okay? Yeah. Okay. So any question for past tutorial sheets or lecture notes that I posted out? 做吗？要做啊，OK，要读啊。So yeah, another thing about your assignments, right? I started look at this few. This course is a pure maths course. OK，就是说要 train 你们怎么写 proof。OK，so 你们要注意一下你们的 proof 的写法。OK，so maybe 我 start from next assignment，我会开始扣分，扣什么分？如果你的写的方式，OK。不 formal 我就会扣分，OK 没有解释好我就会扣分，好，这样子。当然了，我在 discuss assignment 的时候，我会告诉你们到底什么东西要注意之后，但是我是想提前跟你讲这些东西啊，因为我不想你好像到了我的 general topology 过后，你还是不懂怎样 proof，已经第3年了，你还不懂怎样 proof，对不对？你都要毕业了，都要走了哦，还不懂怎样 proof，我靠！wasted，对不对？对不对？所以你们现在 second year first sem 一定要懂怎样 prove，不管你以后有没有用，其实你没有用这个 prove 的东西会用在你以后去做你的自己的 project 啊，做你自己的什么 contract 啊，so on 啊，都是有用到的。你一定要写好好的，这条 imply 这一条，这条 imply 这一条你做到这个我罚你钱，还是什么？没有做到我们就毁约。要写好好的吗？不然我怎样知道我们怎样 follow 这个 contract，对吗？一样的东西来的，其实只是我们比较学术的，OK，idea 是一样的。So 我们会注意这个 proof style，还有一个就是你们的 handwriting，OK，请你们务必写大一点，写清楚一点，OK，因为我要改这么多的 assignment，眼睛很累。因为有时候我 zoom 还是很小你知道吗？我已经 zoom 了。不要讲我没有 zoom 了还是小，或者有时候不清楚，我不知道有些 file 有问题还是怎样，它会特别 蒙 not clear。所以你们注意一下，你们 send 上来的时候那个方，好 ，OK， 可怜一下我。Okay, right. So far it's like that. Okay, I mean, let's recap what we did for the past 6 weeks. Let's recap what we did for the past 6 weeks. Where did we start at first? Do you guys still remember? We have a real line, right? We built a real line. And then we talk about convergence of sequence. Okay. 他们已经走了多么远了 convergence of sequence. So what's the convergence of sequence mean? Let's say an converges to 8 for n large. What does it mean? So your a is your limit, right? Okay, for every epsilon, you can find a n such that when n greater than n, an is minus a is less than epsilon. So this is what it means here. 它跑进去了那个 epsilon 的 range for n large. an plus 2 an plus 3, an plus 4, an plus 5, an plus 6全部在里面了。OK， and 这个不是 word for one epsilon 哦 ，for all epsilon， 意思说什么？我还可以把我的 epsilon 再做小一点。U exist 一个 an 2 maybe， then an 2加1就 within 这个 epsilon range 了。全部不是只有一个，它后面的全部都是。这样的话，我们才可以保证 we can make sure we have the convergence。OK 了 ？OK， 你不可以说哦，远远有一个在这边 maybe n epsilon 加1万躲在外面，不可以的，它一定要在 epsilon gap 里面。Make sense? Okay, so this one cannot exist. Okay, and then so I mean 这个东西我们可以怎样表示 ？Okay, how we can rewrite this? Actually, we can rewrite this as a function, right? Function from n to r. 那么这个有一个好处，那么这个有一个好处，它好处在哪 ？Why we did this? So the epsilon height here will become something in the vertical. Epsilon a, something in the vertical. And then all the a1, a2, a3, an terms are on the horizontal. Okay, so maybe, how should we put this? So here, let me move this out. So n here will control which term you have. Right? And then the epsilon here will become somewhere in the vertical here. So let me put it like this. A plus epsilon, a minus epsilon. Okay. And then how do you see that an converge to a? So meaning for some an, these terms have to lie inside the epsilon gap here. So let me draw this line out. So where's the epsilon gap here? Somewhere like this. So for example, this example, for which n? Okay, for which n? An greater for little n greater than n, an is minus a less than epsilon. For which n? What n works here for this example? What's the n epsilon that works in this example? What do you think? 3. For example, 3 works. Actually, 2 also works already, right? Because we have little n strictly greater than n epsilon. Strictly greater. Strictly greater than the next term is 3. 3 already inside. If you want to pick 5, can or not? Can or not? Pick 5, can or not? Also can, right? Because 6, 7, 8, 9, 10 also in there already. So pick 7 also can. Okay, so the point is that exists. Exists is enough. No need the special one. Or no need, yeah. Exists is enough. Okay. But this picture where it looks a lot like what? A lot like what? This is a function, right? But what if you consider function from R to R? Okay, so this is where last time we stopped last time, right? This is where we stopped last time. We transform this epsilon n convergence to a epsilon delta convergence here. Okay, no, not convergence, continuity. So we extend this idea to epsilon delta. So let me draw some example out. Okay, so let's give us a continuous function like that. And then let's fix some point. Okay, maybe we call it C. Okay, so here is a FC. So let me like that. C. Okay. So C here, and then FC here. Okay, so what is the epsilon delta here? What's the epsilon delta doing here? So let's write down what this epsilon delta continuity says. So let's say it is continuous at C. So what does this mean here? Recall the definition. For every epsilon greater than 0, there exists some delta. Then what does this delta do? Such that for every x in the domain of F, if the distance between this x with your C is less than delta, then what happened? Fx minus Fc absolute value is less than epsilon. Okay, so what does this mean? So what's the main thing you want here? What you want is when does the Fs minus Fc less than epsilon? Okay, remember our goal is at the back one. Okay, so what do we want here? So what we really want here is, let's say we fix an epsilon here, Fc plus epsilon, Fc minus epsilon here. So we want to ask, okay, how far the x around C can make sure this the fx is within epsilon distance with Fc. Can you see where is it or not? As long as I fix my delta like this, right? So I fix this as my delta, and then here maybe minus delta. Then I can make sure, wait, so let me use another color maybe. So I can fix this delta so that I can make sure that all this fx is epsilon within my Fc. Can you guys see or not? Can you guys see what is happening? Here is x plus epsilon, x minus epsilon. Can see?
Note that I cannot pick my delta up to here. Why? I cannot pick my delta up to here. You know why? If I pick my delta up to here, what happened? What are all the fx for the x in between x minus delta 1 and c? Huh? Not within the epsilon distance. In particular, which part? Which part is not within the epsilon distance? This part here. Okay. This is the part that's outside. Okay, so we cannot pick this delta 1 here. So it makes sense or not? Okay. So can you see the similarity between these two or not? The similarity between these two. Okay. So you can see that epsilon is like governing something on the y-axis, the value. And then n tells you how far you can go. And then also delta tells you how far away from C. But the point here is C is a limit point. Okay, but at the top there, n is like keep increasing. Okay, but at the bottom, we have two sequences actually. One sequence is on FC, the other sequence is on C. Okay. Can you see the similarity? Okay, please see this similarity and then go back and see the proof again. Okay, the equivalence proof. It's very important. How important? Important until I put this question in your tutorial question. Okay, so in the tutorial question this week, I asked you to prove limit. I asked you to use 5 methods to prove it. Okay, first method is you use your calculus way to do it, limit law. Second method, you use sequence to prove it. Okay, let me show you the question first. And probably we won't do it today, but we can do it on Saturday together if you. Let me open out the question. Anyone look at the tutorial question for last week? Tutorial 6. Yeah, this question here. Okay. First, you use limit law to compute what's the limit. Second, use epsilon n definition, which is the sequential definition Sn converge. So you create Sn converge to 1 and then show that this one converge to your limit. And then use the epsilon delta also. Okay. This one is to prove limit only. And then another question I asked you to prove whether this function itself is continuous at this limit point or not. Okay, using epsilon delta, using sequential. Okay, I want you to write out all the proof and then you compare what is the similarity between them. Okay, you can try and do it and we can discuss it on Saturday also. Okay, after this example, I think it's pretty sure, pretty clear what are the difference between these epsilon delta and sequential continuity. Okay. And then go back and read the proof again. And then I think the proof will make more sense. Yeah. I think this example is quite important for our course. I think this is the core thing happening in our course. Afterwards, if you do integration, if you do differentiation, it's just all this. It's just we look at the limit of different functions. Okay, but the central idea is like this. You look at the sequence, you look at epsilon delta. Okay, no. Okay, so this is very important. This question. Once you do this, I think you can almost get what is happening in the whole course already. Does it make sense? Okay, no. Make sense? Okay, this example very important. Yeah, try and work it out at least. And then you will pretty clear what is happening in the whole course. Okay. Right. So where did we stop last time? Last time we stopped at I haven't finished recapping. So last time we proved that fx equals to x squared is continuous. Right. We proved that x equal to x squared is continuous. How do we prove that? Remember? How do we prove that? Where is it continuous? When we say continuous, I didn't say point meaning what? It is actually continuous everywhere. Okay, at all points in the domain. In particular, the domain of fx is R. R. So we fix any x, and then we fix epsilon greater than 0. Okay, then what do we do? How do we find the delta? Remember, we do some trick here. What's the trick we do here? We choose delta to be the minimum of what? Of 1 and something else. What is that thing? Epsilon over 2 times the length of x plus 1. Why did we do this? I remember. Why do we do this? You want to make sure what? Then for every y in R such that y minus x less than delta, what do we get? We need to compute such that y squared minus x squared is less than epsilon. Okay, so how does this 1 here help us? How does this 1 here help us? We can rewrite this y squared minus x squared to be what? Y minus x times y plus x. But you see, y minus x here, I make it less than delta. But how to control y plus x here? How we control y plus x here? Yes. So we just consider all the y. That is, so let me draw here. So we just consider now the y. We just consider y plus x less than 1. So how should I draw it? Let me think. So my x is here. I fixed my x already. And then where is my y? So my y is either x minus 1 or x plus 1 away. Okay, so I just fix my y around here. What does this mean? What does this mean? So, I mean, let me draw this using different color so that differentiate. So, for example, my graph, let's say this x is positive, right? Let's say this x is positive, and then we got a xy graph here. And then what is x, fx equal to x squared? Fx equal to x squared looks like what? It's like maybe something like this. Maybe draw a bit fatter. Okay, let's draw it fatter. Okay. So what are we doing here? We set our y minus y to be 1 away from x. Okay, to be 1 away from x. So that the epsilon we look at here is where? We are looking epsilon around this fx here. So the epsilon is maybe around here. Okay. So as long as I make sure my x is in between this delta, then all the fx here will be within the epsilon distance from fx. Make sense or not? Okay. Because if you make this x bigger, if you make the delta bigger, then you need to choose a different choice of delta here. Okay, so how this works again? So let's say this is less than, so this part here, we have epsilon over 2x plus 1. So if I make y plus x is, sorry, if I make y minus x is less than 1, then this implies what? Y plus x is less than 2 times the absolute value of x plus 1. Okay, so you see, the delta here is making sure how close is y and x. If you make y and x close enough, right, then you imagine I want to add y and x together, how large it can go. How large can it go? Huh? How large can it go? At most 1. You add up, you add up. So the difference is at most 1. But now you add them up. So it is 2 times x plus 1. Okay or not? Okay. Yeah, actually, you should prove this if you are in doubt. I think we did a similar proof on this kind of thing. Yeah. So what you should imagine first, to understand this statement, you need to take your y within this one gap here, and then try and take the largest one, add it up. The largest one is what? X plus 1, eh? X plus 1 plus x, 2x plus 1. No? Okay, maybe you ask a question, why you want to put absolute value here? You need to imagine this x maybe happen in negative part. Right, negative. So how? So if forever I take positive, then definitely this number is greater. Right. Absolute value x must be greater than minus x. Greater or equal. Okay or not? Can you think like that? This is a way of thinking it, but you need to prove it. Okay. Before you prove it, you need to make sense of this segment first. It's better. Okay. So once I get this inequality here, what happens? What happened? I have absolute value of y plus x over 2x plus 1. So the quotient here is something less than 1. Right? This is something that less than 1. So this quotient here is something less than 1. So you multiply epsilon with something less than 1. So you are less than epsilon. Okay. So remember that last time Jinsen also said that I can pick delta to be other thing. Right. I can make my delta longer a bit, maybe around 2. Can. Then you need to pick a different choice of epsilon over maybe. So this condition here will change. So let's say if you make, so this one is a lemma 1. So lemma 2, this is lemma 1. About lemma 2, what if I make this distance less than some n? What happened? Then what happened to the absolute value of y plus x? Then it is just less than 2x plus n. That's it. Yeah, you can pick a higher one. It's fine. Okay. So, this is not just the only way to solve it. Within this way, we already have like infinitely many cases already. Okay, you can use multiple way. So this is the difference of pure max. Okay, we can accept different answer. And I show you the other answer now. I also can pick my delta like this. This one not involving minimum, just involve epsilon and the point that you want to check. Epsilon over square root x squared plus epsilon plus absolute value of x. Why it works? Then you need to go and compute. You see, the first line of computation is the same. Can you see that? This line of computation is the same. Okay. If I pick this to be my delta, what happened? I need to bound y minus x by this delta here. Okay. And then how about this part? This part, there's no y minus x. So I need to create y minus x, y minus x out. So once I create y minus x, I got 2x coming out. Okay, once I bound my y minus x using the new delta here, then I got this extra plus 2x here. And then I combine everything with somehow the top, the numerator and the denominator just differ by a factor of delta, epsilon. Then I got epsilon outside here. Maybe you want to ask me, hey, how you come up with this genius delta? How do I come up with this genius delta here? How do I come up with this genius delta? What am I solving here actually? What am I solving here? I'm actually solving this equation, you know. I'm solving this equation. Delta times delta plus 2x equals to what? Epsilon. Correct or not? What is this delta thingy? This delta thingy is something when you multiply to exert plus 2 modulus x, you get delta. And you solve this, then you will get the expression of delta. Correct or not? Because you are solving delta with respect to modulus of x and epsilon. You see your delta, everything inside is epsilon and does it make sense or not? You want to find this delta such that this calculation work. Okay or not? But this is not what I required you to do in exam. Okay, this is like perfect delta. You can do just the minimum one is enough. Okay. But if you can do this one is like the perfect delta. Why do I say this is a perfect delta? Why do I say this delta is perfect? Sorry? Yeah, sure. Only want to consider. Actually, there's another viewpoint here. So it is the largest possible delta you can pick for every epsilon. It is the largest one you can pick. Because you make it a bit larger, then the epsilon thingy will fail. You know, this is the largest one you can pick for every epsilon. So what does it mean? So let me show you. Let me show you the epsilon graph of this guy. Let me copy here. I did put the remark. You can read it later, but I want to tell you what is going on first. So what is this delta doing? Let me show you here. Okay, so what does the delta do is you pick an x, okay, you put one x, and then you put some epsilon. For example, the point here that pick 1 here, okay, and then you pick some epsilon, maybe you see epsilon minus, so epsilon equals to 0.2 here. So here is the epsilon equals 0.2. Okay, so this gap here. Okay, so for a fixed p, what does the delta did just now? It picks up this region here, the whole region. Is the largest one. If you go out a bit, then you won't have this epsilon gap satisfied. Okay, that is what the epsilon delta did. But what does it do with our delta? What does it do with our delta? what we did for our delta is we randomly pick like delta equals to 1. Okay, or delta equals to some random n. Okay. But what the delta we picked just now is the exact delta that will do the epsilon job. Does it make sense? No. Okay. 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 And one more problem here. One more problem here. What can you see from this equation here? When you pick your x far, x the position of x in your function very far, 1 million. What can you see in the x square function? What happened to the x square function? Y equals to x square function. What happened? It become steeper, steeper, and steeper. And this is what this delta tells you, you know. When x get large, this delta getting smaller, smaller, and smaller. Meaning what? If you put the same delta, if you put the same epsilon here, you see, if you pick the same epsilon here, epsilon minus epsilon and minus epsilon and minus epsilon here, you see, epsilon minus epsilon here. Maybe you pick 1 point. Maybe pick the middle one, right? So to see the differences. You see, the delta for the lower x, or maybe this one is x1, and then this one is x2. For x1, how large is the delta you can pick? Maybe you can pick this delta here. x1 plus delta 1, x1, sorry, this one should be minus x1 minus delta 1, x1 plus delta 1. But how about around x1, s2? It is like somewhat smaller. So the further the x be, the delta that will satisfy for the fx minus f, let's say fp for the point less than epsilon is getting smaller and smaller and smaller. Okay or not? Okay. 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 So you can see the observation. Everyone see the observation? When x far, you only can pick smaller and smaller delta. Okay. That works. Okay. So far, any question? Question about this? Actually, this phenomenon also gets seen from here, right? Also gets seen from here. You see, your delta also depend on x. If x get large, then this delta also gets smaller. Only very close x can satisfy the epsilon gap when you go further and further. Okay. Okay, so far any question or not showing this? So there are few ways, a lot of ways to do it. So, okay, so I think I also posted up this question, this example. So you can see that if I set different epsilon, you can see the delta changes. Delta changes around 1. Okay, you can see that the delta changes. What can you see? When the epsilon is small, right? The delta will also get smaller. Okay, when the epsilon get bigger, you want to check how many fx satisfy this range. The x that satisfy also get larger. For this case, Okay, do you guys know how to read this example? So there's like 3 delta here, 0.2, 0.5, and 1. And then you can see that what are the that satisfy this epsilon gap here. Okay, so let me see. Right, close this. So you can see that can I make more line? Let me pick. So this one is the delta 1. delta 1 box look like this. Epsilon 1, sorry. Epsilon equals to 1 looks like this. And then we also got epsilon equals to 0.5. So maybe it look like this, 0.5. Box here. And then there's one last one is 0.2. So 0.2 is like here. Okay. Yeah. Can you see it? Like different, same color to you. Is it look the same to you? Like this side better or not? Yeah. Okay. I think it's better in the lecture notes. I put into the lecture notes already. Any question on how to read? You must know how to read this picture so that you will get what's the epsilon delta doing. This is the exact picture we are talking in the definition. Got question on how to read this picture? Can understand what this picture doing? Okay. Yeah. Okay, good. We recap for 1 hour. Okay, so before we take break, I think we should do something else first. Right. So so one last thing to recall here is, I guess, is the limit definition. So I think we need to remind you what's the limit. So limit for functions. Okay, last time we talked about limits on sequence, right? Okay, so now we also talk about limits on functions. So what's the limit of function means? You can recall or not? When do we write limit x to p, for example, fx equals to fp? Okay, what does this mean? If what? There are two equivalent definition also in this case. It's similar to continuity. Okay, later I will show you what's the differences. So let's say first one we put sequential definition. So this one is sequence. And then the second one is epsilon delta. Okay, we have two definitions for this as well. Okay, so that's why I asked you to do it in the tutorial. Proof using 2 ways. So first way, sequential. So what's the definition of a limit? If for every sequence of points of Sn such that what? This Sn can equals to P or not? It cannot equals to P. Okay. Such that if this sequence is not equal to P but in your domain, and this one is for all n, and Sn going to P, then what do we have? We have fxn converge to f. Okay, so this one is better than your left and right limit. Why? Because this one consider any sequence that converges, not just coming from the left, not just coming from the right. So it comes from everywhere. It could come from left, could come from right, come from everywhere. Okay, as long as you have xn converge to p first. Okay. And then how about epsilon delta definition? What's the epsilon delta definition? If for every epsilon greater than 0, there exists a delta such that what? Such that for all x in df with what? With x minus p is less than delta, also greater than 0. Because we don't want our sequence to have point in to be equals to p. I don't want to know what is exactly happened at p. That's fine. Okay, I just need to know what happened to nearby p. This is the sequence we are talking about at the top. The sequence also doesn't include p. No need to include p1. Okay, I just want to know nearby p. Okay, so that's why we call limit, man. It's not exact, man. It's limit, just limit. Okay, I will just look at nearby p on it. And then this will imply what? This will imply that fx minus fp is really close, so less than epsilon. They are difference. Does it make sense? So so the last exercise, we are quite tired last time, right? The last exercise I asked you to do is to show this equivalence. So to show the equivalence between these two, right, it's really similar to showing the sequential continuity and epsilon delta continuity. What's the difference? What's the difference of this line with the epsilon delta continuity? What's the difference? Where's the difference? Yeah, only this part only. This one throw away, then it's the continuity already. Make sense? Okay. So this limit here is extra big here. I don't want to consider the point at P. Okay. So it's really similar. The top there also also similar, right? The difference is just the Sn we can take equal to P when I'm I'm considering the sequential continuity. Okay. So the difference is just throwing away the point P, okay, when we consider the convergence in the domain. Does it make sense? Okay. Yeah. Try and show these two equivalences. It's the same way. Really, it's the same way as epsilon delta continuity. You should try and do it. Okay, speaking about this, we can finally introduce this theorem here. We have squeeze theorem for sequence. We also have squeeze theorem for function. And we have squeeze theorem for function. I think we will briefly talk about this. So do you want to guess what's the statement of squeeze theorem for function? Want to guess? First of all, you need to start with tree function. Okay, so what happened to this tree function? What happened to this tree function here? Remember what happened to the squeeze theorem in the sequence? You got three sequence, and then one sequence is bounded above and bounded below by the other two respectively. And then if the two converges, then the middle one also converge. In this case, if you have three function, then suppose what? Okay, suppose G is bounded below by fx and bounded above by hx for all x in D, then what? Then what? Then what? Okay, so to talk about convergence of f, right, we need to have a, suppose P is a limit point of D. Then we will say that then limit of x to P fx If the two bounded, okay, sorry. If f and h converges at a point P, then we can also say that we also can say that's what? We also can say that the middle function also converges at P. Moreover, it converges to the same limit. Make sense or not? Does it make sense?
Next one will be yes. Thank you.
Does it make sense? Okay. So if you are bounded by two functions which is convergent, okay, convergent, then the middle function also converge. But the conversion means what? You have a limit at a point. Okay. You have a limit at a point. So if you have a limit for fx at P, if you have a limit for hx at P, gx also has a limit. Same limit. It's similar to convergence sequence in yeah, is it similar to the convergence sequence? You are squeezed by two sequence, okay, and then the two sequence converges, then the middle sequence also converges to the same thing. That makes sense? Okay. How to prove this? Prove this. Definition of just now, you need to take you can take either one to prove it. Okay. You can take this to prove it. If you take the sequential definition to prove it, means what? For every sequence that is not P but converges to P, you want to show that G of Xn also converge to L. But what? But you can take this sequence and then apply F and H, right? Can you follow me, or do I need to write down? Did I write it down? I write down. Let me write it down, and then I think you should see something. So we want to show that limit x to P, gx equals to L. Okay, so what does this mean? For every Sn that converges to P, such that such that Sn not equals to P for all n, we want to show that G of Xn also converge to L. Okay. But what can we do? Take such Sn that converge to B. What happened? We can look at what is Fxn and Fxn and Hsn. What happened to these two? What happened to these two? What happened to these two? Maybe I also have Gxn. What happened to these three? How I put them together? What's the condition I have for F, G, and H? Less than equal to Gx, less than equal to Fx for all x in D, right? But where are these Sn from? D. These sequences are from D. So what do we have? We also have Fsn less than equal to Gsn less than equal to Hsn for all n, because what? Sn are all in D. And then by assumption, Fsn converges to where? L. HSN converge to where? L. And then G have to go where? Why? Why GSN have to go to L? What rule? Squeeze. Squeeze theorem for who? For convergent sequence. So you see, squeeze theorem for function reduced to squeeze theorem for convergent sequence. Okay or not? Okay. So that's why I say sequence very important. What we build afterwards, everything is coming back to sequence again. So you need to really lay the foundation inside your sequence. And then what you do afterward is applying what happening we proved just now. But I give you a task here. I give you a task. Can you show squeeze theorem using epsilon delta definition or not? Okay, try and prove it using epsilon delta definition. Okay, try exercise. Okay, exercise. Prove squeeze theorem using epsilon delta. Okay, once you do this, you will appreciate why there's an equivalence between the definition of epsilon delta and sequential limit. Okay, epsilon delta limit and sequential limit. Once you do this, okay, you can see the equivalence happening in the proof of squeeze theorem using convergence theorem and then squeeze theorem using epsilon delta. You can see, okay, you can see what is going on. What's the equivalence proof there? If I'm free, I will write out this proof, and then you can compare. Okay, no? Okay, yeah. So yeah, so this is an example of equivalences of between the definition of epsilon n and epsilon delta. Okay, no? Maybe let's see. Okay, maybe we'll take a break and then we return with uniform continuity, and then we dig some monotone function, and then we will finally left continuity. Okay, let's take a break now until 1:09. Yeah, you guys can have a snack.他不一定，他没有。对不起，你不用问他，你不用问他，要给我了。他会。好的，他说好的，好的 ，OK。你没有问他新公司吗？啊？有没有新公司？店面新公司，要不要去管理？会被开定，完了，对面还有一个，这个。接触球，人球还要掉一头，一盘用完，也是没完全的，还没有融化，这件事，然后这个，哦，有的，开始了，开始了。他是还脸抽的意思，是的。 要看鬼片啊？
累啊，
啊，
累啊，
累了，看鬼片，可以，然后我们看鬼片。他你是他的在对我，把自己把我体会不想到，是的。你过来先习惯。哦，是。今天还可以吃的。很苦了哦，很苦了，不是太苦了，不是嘞，啊，不是，太苦了。这个是滚动，这样这样，开玩笑。不能买，还可以买，现在不能买，但是我是以前买，然后用了，我有买2次，
买2次，
因为我怕它不要更新那个功能。
一样的，你还可以用还是用，它是变成不断6了，但是你还可以用不到，
哦，
就是你不能用不到6岁那种，刚好可以分3个小时，
对，
变成一种平台，好像还可以。
说它叫什么 AI
没有，现在没有，
感觉没有，
没有。它 AI 只有 specific 话吧？有声音，有声音，
可以看，
有大家。要把 texture 加上去，然后跟到越来越长的。
这个
不过
这里也是的，
为什么只有Samsung 才有？
现在你买还是？
这是免费上的。
不要。
年轻的时候，
这样的。
年轻的时候很穷，但是努力了，对，年轻的时候很穷，努力了几年，终于不年轻了。
然后呢？
没有，就是本来年轻的时候很穷，然后努力了几年，
还在。
终于不年轻了。
哦，那我看到了。本来要把熊弄掉，结果把眼睛弄掉了。别打，别打。感觉有犯错一点。
年轻的时候就要多吃苦，老的时候就会习惯。
哎，我有 send 过你个面，那个煮饭煮面的，老板也有面忘记加盐。哦，对，我看到，就忘记讲嘛。然后那个老板就流汗，他惨了。然后后来他来了一句：“爱你无比多。”
啊，对。
买这个东西有想很久了，我有研究了，有趣，看到就买。这个好，这是最 flagship 的那个，基本的，这好像是 flagship 的 flagship 叫，就是 iPad Pro level，
还有个大家
大件罢了
啊，还有分就是大家哦，
它的里面一样，
像差不多，就很像 Pro 有分11个13寸这样子。
所以就是好。
OK，maybe analysis 有点闷，我们来看一些 anime，未来，不知道你们有没有看过《Demon Slayer》鬼灭之刃，Demon Slayer 出了新的，真的是昨天，什么问题？没问题。但是有一个小片段，我想 share 一下，因为我一边改 assignment 的时候，一边有感触。share 这个 part。说《鬼灭之刃》about what？哎，你们全部会看 Chinese subtitle 是吗？对不对？OK，鬼灭之刃》about what 呢？就是有一堆人想要杀鬼，鬼是坏人。OK，一堆人，现在这一堆人在开会，要怎么杀鬼？OK，呀，听一下他们在开会的时候讲了什么东西。我应该没有剧透哎，剧透一点啊。OK，这一段我觉得很有意思，你们看一下，看清楚啊，这一段他们在做吗？很有意思这一段。 Hello testing，呀，这个只是一部分吧，这一集有来1个小时，OK，看得懂吗？刚才在做什么？看得懂吗？谁可以解释一下？没有，不用看得懂，来看到什么？I recall， recall， yeah，讨论怎么触发那个印记，怎么讨论呢？他问会的人嘛，对不对？所以有2个人会嘛，一个是女的，一个是男的嘛，对不对？所以这2个人怎么解释他们得到这个印记？女的讲什么？一种感觉，yes，总体来说是来感觉，哇，我感到很兴奋啊，心跳很快啊，诶，就有了咯，哇，有了我就很有力了咯。OK，但是男的呢？男的怎么解释？男的怎么解释？耶，条件，而且这个条件是可测量的条件。你心跳有没有跳快过200？你的体温有没有39？OK，所以我要讲什么这边？所以这个有一点像我们在学数学哦。OK，prove Bolzano-Weierstrass. Every convergence sequence in a bounded, every bounded convergence subsequence. 所以一种人讲 proof 呢？你 bounded 吗？bound 了你的 sequence 就在里面嘛，对不对？And then somehow 它就越来越小，越来越小咯。你可以找到一个可以 converge 的 subsequence 哦，就找到了咯。把我们 proof 怎样 proof 呢？我们先切一半，再切一半，再切一半，再切一半，一直切，切出来的这些 sequence 会 converge 去那个点，then 那个点就是我们要找的 convergence subsequence，你懂吗？get 到我要讲什么吗？明白吗？所以如果我们学了数学，不是我们的解释就要有点像那个是叫做霞柱那个男的 Miss Hashira 霞柱。就我们要有 scientific 一点解释，而且哦，这2个人解释的时候，你可以看一下，那个女生是花柱来的 flower hashira，所以她解释的时候，那个图案里面啊，就她自己罢了，没有别人的存在这样。但是呢，那个霞柱在解释的时候，他说：“哦，我看到那个少年要死了，然后我回想我的以前。”然后他问他，哎，怎么你知道你的温度是39度的？哦，因为那个护士姐姐帮我测过我发烧。You get what I mean？所以你的 explanation 呢、是要可以去 connect 别人的，而不是你自己讲你自己爽的那种。OK 了呢？OK 吗？OK。OK，actually 啊，还有一个 side story between 这2个，就是刚才 close 要结束的时候，不是也有一种人出现嘛？他听了过后，哇，其实很难达到的东西，不是？但是那个叫做封住你那个疤那个，他讲啊，这样容易就可以了，然后他就以为哇，这样子全部做一下就可以达到了。但是问题是哦，要做这些东西哦，不是一件容易的事，对不对？所以呀。说呀，很多东西啊，就是呀，anime 不是看爽，不是看美，不是看漂亮，有些 anime 里面有那个 philosophy 在里面，他把真实的事件写进去，真实的人的事。OK，OK 了的，可以吗？So be like 霞柱，be like 霞柱，OK，OK 吗？OK 啊，All right。呀，这个 anime 蛮好看的，你们可以自己去找找看。呀，Demon Slayer。一个是他的画风好看啊，一个是他故事线也好，都很好，It's very good 啊。上次我给你们看那个《Jujutsu Kaisen》呢，这次我们给你看《Demon Slayer》。好，下次 看看还有下次。啊？分一半啊，2.5条路啊。OK，next time 我们学2.5条。2.5条路。可能如果来得及的话，我们可以一起看 One Piece 的大结局，我们可以讨论一下。One Piece 大结局很有意思，应该。Okay, let's see. What else we want to talk about? Okay, so let's talk about uniform continuity now. Hey, where is Ivan, by the way? Ivan also disappear. Ivan. Ivan? 啊，我也知道。OK，我想问他在哪 ？Sleeping. Okay. All right. Let's continue. So, a function f on the domain, okay, is called uniform continuous. So, we first time see this uniform. What does uniform means? Uniform means what? 效一啊。Uniform is what? 为什么效一叫 uniform? 平整，因为每个人都穿一样啊。Uniform 哦 ，uniform 就是一样。OK，uni 嘛 ，uni 是一 form 一个形式，一个形式。OK，uniform。So 这里的 uniform 是什么？哪里 uniform？OK，let's see. So epsilon for every epsilon greater than 0, there exists a delta， 这个很正常。Such that 这边就 difference 啊。Such that what? For every xy in df, if x minus y is less than delta, then fy minus fx less than epsilon. 这个意思是什么？这意思是什么 ？What does this mean？ 这里我们没有 fix 一个 x 先了，之前我们 fix 一个 x， 这里呢，所有的 xy 只要 if it is less than delta， 所以 uniform 在哪里？这个的 uniform 发生在 delta， 一种 delta 可以 work for all xy such that fy minus fx is less than epsilon。每一个 xy 只要用一个 delta 就好了。刚才你记得 ，Do you still remember the x square example? When the x large, what happened to the delta? Become smaller, smaller, smaller. But this one, uniform. If you have the same epsilon, no matter how far you move this epsilon, big X, still within the same delta, it will work. Okay, so how does this work? So let's give you an example. I give you an example. So just now we have a non-example. So non-example, first non-example we have seen already. Fx equals to x squared is not uniformly continuous on R. Because when we move point far, for the same epsilon, the delta will get smaller and smaller. Okay, not one delta can work for all. But if we make fx equals to x squared on, maybe let's say the closed interval 0 to 1, then fx equals to x squared is uniformly continuous on this closed bounded interval. Okay, let's prove this. Okay, let's prove this. So now we fix one epsilon. Okay, and we want to find delta greater than 0 such that if x minus y less than delta, then x squared minus y squared is less than epsilon. Okay. So let's do the working first. Okay, let's do some working. So similarly, x squared minus y squared equals to what? X plus y times x minus y. Okay. Okay. So we want to find a delta that works for all points inside 0 and 1. Remember what's the problem with bounding x plus y just now? We don't know where our x and don't know where our y is. But now, where is our x and y? In between 0 and 1. So what's the largest number for x plus y? 1? Yeah. Could be both 1, right? So 1 plus 1 is 2. So on this interval, so since x and y, we already bound them. Then there's this term less than 2. And then this is less than 2 times absolute value of x minus y. So I just set, what should I do? I just set x minus y to be epsilon over 2 to get epsilon. So meaning what? So meaning I just choose epsilon to be, delta to be epsilon over 2 so that if the absolute value of f minus y is less than delta, then what? Then the absolute value of s squared minus y squared is just x plus y times x minus y plus, but x plus y is already bounded because our xy is taken from the interval 0 to 1, so I get 2. And then this is multiplied by the difference of x minus y. And this is simply just 2 times delta, where delta is equals to epsilon over 2, which is epsilon. Okay. Okay or not? Okay. Okay, there's one thing I want to remind you. In your assignment, right? I know you need this working, but please don't write this working for me. I don't need this working. What I need is this proof. Okay or not? From this proof, I can know what's your working. Does it make sense? Okay, no need to give me this in your assignment. What I want to see is just the proof. Does it make sense? You can put your working at the back, but please don't combine with your proof. Does it make sense? Because why? From your proof, I can already read your working. Can you see or not? Your working actually hide here. Does it make sense? Okay, it's just the way of presenting now. Okay, I want you to learn a proper way to present. Okay, I don't care how you work it out. I just want to listen how you present only. From your presentation, I already know what's your working. I don't need to ask how you do this. I can see from here already. Does it make sense? Okay, so you just write the blue part. No need to write the green part. Green part is for you to work out the blue part. Okay, I just need to see the blue part. Does it make sense? You see, did you notice that this blue part here already included what is in the green part? But it's the way of presenting is different. Okay, make sense? Okay, okay. Please, don't write working in your notes, because I want to see proof. Okay, this one keep here. This one I make a remark, not for assignment proving. Okay, for your own calculation. You can keep it in the back, but don't keep it in your solution. Okay, so what do we see here? So we can actually make a theorem here. quickly deduce a theorem. Can you deduce one theorem from this example here? Can you deduce a theorem from this example? When is a function uniformly continuous? So you start with a continuous function. Let f be continuous. S squared is continuous, right? But we just consider it on a closed and bounded domain. Okay, just closed and bounded domain. So closed interval is closed and bounded. Then f is uniformly continuous. Okay, so this is how we build theorem. No? We see from one example, and then we pick out the characteristic, and then we want to show whether this is true or not. Okay, so what does closed and bounded means here? Let's remind ourselves. Bounded means what? Bounded is easy. So for every point in the set is bounded above and bounded below. But what is closed? Closed is a little bit different here. Okay, closed means what? Last time, the very last example we introduced is set is closed if it contains all the limit point. Okay, if it contains all its limit point. What is limit point? What do you mean by limit point of a set? Limit point. I think we go quite quickly last time, so maybe it's good to remind ourselves. We didn't put very much effort in understand or proving it because we will not use the definition frequently. But we just want to use one property is if we say a domain is closed, then it contains all of its limit point. But what is limit points here? So last time we talked about limit point, right? Isolated point, remember? How to be a limit point, how to be an isolated point. So if C is a limit point of DF, then what? Then there exists a sequence that's not C, but converge to C. Remember? We take a sequence which is not C, but converge to C. Because you can simply just take a constant sequence that converge to C. Correct or not? C constant function on C. Okay, so if there's a sequence which is not equal to C, but converge to C, then you are the limit point. So can we quickly see why the closed interval 0, 1 is closed? Why it contains all the limit point? Why it contains all the limit point? Hey, did I show it here or not? Right. I did show it. So show that a closed interval AB is closed. Okay. So what do you need to show? You need to show that the closed interval AB is equal to the limit point of AB because it contains everything. Okay. So how to show? So first direction is you want to show that every point in the closed interval is the limit point. Okay, so meaning you need to what? You need to produce for every point in your closed interval, you need to produce a sequence which is not equals to the point, but converge to it. Right, so you see, there are three cases here. Why there are three cases here? I just split it into the left endpoint, right endpoint, and everything in the middle. Okay. If it is on the left endpoint, what can you create some sequence that converges to it or not? So I think it's better we draw something here. So let's say we draw like this. Here is A, here is B, maybe somewhere around here is X. Okay. A, can you create a sequence that converges to A, which is not equal to A? Can or not? Can or not? What sequence can converge? A plus B minus A over N. Why? Can I do A plus 1 over N or not? Can, but who knows this 1 over n is outside? Eh? You get what I mean? Because b minus a is too small already. So that's why I put a scalar here, b minus a over n. Okay, so I will make sure that this b minus a over n is inside this region. Okay, so this will converge to a. And then similarly, you can do b plus a minus b over n. So it will be some point converging to b. In the middle, middle is the same. You just start with random sequence that converge from b, or you want to converge from a also can. Okay, and then this is just showing that every point is every point in the closed interval is a limit point of AB. But how do you know that you already achieved all the limit points? You need to show that for all the point outside this closed interval, it is not a limit point of AB. Okay, make sense or not? Okay, meaning R slash this closed interval is not a limit point of AB. Then you done. Okay, so for any point not complement, in other words, in the complement of a closed interval, it is not a limit point. Okay, so you can show it this way. Because if it is slightly, for example, slightly less than A, so let me draw again the picture. So maybe I got A here, I got B here. If it is slightly less than A or slightly greater than B, what happens? There is an epsilon gap here. What's the epsilon gap here? It's simply x2 minus b and a minus x1. Okay, so there's an epsilon gap here. So can you still converge or not? Using the point inside AB. Can converge or not? Cannot. Does it make sense or not? Okay, because you cannot find any more points in between here. No points. There's no point. No point here. Because all your point is inside the interval A and B. So you just set this epsilon, then there's no n such that an will works, such that the an will be epsilon 1 within x1. Okay or not? Try and write down this carefully. I already write down it carefully. You can try and read. So for your beginner stage, this is very important, beginner stage. So you should think as yourself as a pure max baby. Pure max baby. Okay, you are baby. You don't know how to walk yet. So what to do? You read first. Okay, cover it. Write yourself. Stuck. Read again. Cover it. Continue. You need to repeat this process. It's like you walk, ma. You ever see how baby walk or not? Learn to walk. Have you ever seen it? I suggest go and see it. Maybe go to Seng IG, you will see it one day. Seng every day show baby IG one. So how they walk? How you walk? Do you remember how you walk? 很少啦，很少 baby 是这样子一站起来就走的。我们称这种 baby 是天才。OK，normal baby 是怎样？他先跪先可能，他先站先可能，他先站了走一步，哇累了又抓住又下来了，可能累啦，可能他没有力也什么这样，明白吗？你不是一下子就可以这样走很快的哦，走从宿舍走来学校，从学校走回宿舍，不是的，不是，对吗？你可能连翻都不会翻啊，以前，对吗？所以一步一步慢慢来啊，慢慢来啊。你就是走起来跌一下，可能走2步又跌一下，走3步又跌一下，但你现在才不会跌倒啊。你明白吗？明白吗 ？Make sense？ then 这个就是 how you learn pure max 哦。OK， 没有一下子就会的，没有这样的，这个我们叫天才。我也不是天才。OK， 所以我们就是要一步一步学罢了。OK 呢？无止境就是不停的学。OK。 All right. So where have we been here? Okay. So we discussed about this closed and bounded. So we want to prove uniform continuity. So how do we prove this? How do we prove this? For epsilon, for every epsilon, you want to find a delta. But here the f is random f. Random f. Continuous random f. So it's quite wide. Quite wild. Okay, so we will argue by contradiction. Okay, we will argue by contradiction. So suppose for the sake of contradiction, is not uniformly continuous. Okay. Suppose for the sake of contradiction, f is not uniformly continuous. Then what? Logic or negation. So there exists a delta greater than 0 such that for every delta greater than 0, there exists x, comma y in df such that if x minus y is less than delta, then but fx minus fy is less than, is greater or equals to epsilon. Okay. Okay, so we got this. So we want to do contradiction. Contradicts what? What's the contradiction here? There's only one condition you can contradict, right? Which is what? Other than closed bounded domain, f is continuous. Okay, you can contradict that f is not continuous. Okay, so to show that f is not continuous means what? Negation of continuity. Also, there exists a delta. There exists a epsilon for all delta such that there exists a x in the domain and then x minus y less than the delta, then but fx minus fy is greater or equal to epsilon. Almost the same, almost. Okay, almost the same. So what do we do here? Okay, so what do we do here? Let me see. So almost the same already. So let's see. What do we do here? So let's take epsilon be given by the non-uniform continuity. Okay. Since it works for all delta, right? So since it works for all delta, then what can we do? Then we can choose delta to be 1 over n. Okay. And we can find Sn, Yn in df such that xn minus yn is less than 1 over n, but their distance is greater or equal to epsilon. Okay. So remember what we do. What are we doing here? We want to show that it is not continuous at one point. Okay, so we need to prove that every point it is not continuous. Every point, at every point, every single point. So how do we build out this single point here? So we are going to build out that single point using this sequence here. Okay, using the sequence here. So you see, xn minus yn less than 1 over n. What is this? This sequence here is like getting Closer, 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 and closer. Correct or not? You imagine x1 minus y1 is what? Less than 1. S2 minus y2 less than 1 over 2. And then 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7. So this xn minus yn is getting closer and closer and closer and closer. But where they converge? Do they converge or not? Don't know. I don't know whether they converge or not. But by Bolzano-Walsh's theorem, why can we do this? By Bolzano-Walsh's theorem, we can pick up what? We can pick up a subsequence. Let's say we pick out from S first, Sn. Okay, we pick out one subsequence. Why can I pick out one subsequence? Okay, I can always pick up one, but this subsequence here is what? Can converge to a point in the domain. Okay, I pick out a subsequence of Sn that converge to some point in Df. Why? Because Sn is live in where? Live in a closed bounded interval, so it's bounded. So every bounded sequence have a convergent subsequence. But if you converge, right? So in this case here, it is a closed domain. So it converges to something inside the domain. Okay, so this limit is inside the domain. So here, because df is close. Okay, because df is close. And also, we can also look at this particular subsequence of y. Okay, what is this particular subsequence here? We will define it to be sjn plus yjn minus sjn. A bit stupid, huh? But why is this good, eh? Why is this good? If you look at any convergent subsequence of yjn, you can always write yjn into this form. Okay. If yjn have to converge, I converge to where? Now, where does it converge? Huh? This jn is following the sjn. Is the same sjn. For example, if sjn pick out the even terms, yjn also pick up the even terms because we use the same jn here. Okay, so this guy have to converge to where? So sjn converge to x. How about this part? The difference here. What happened to this difference? Converge to 0 because this is the term that's large in xn minus yn. Okay, so that part will converge to 0. So this part is always less than 1 over n for n. So this part converge to 0, and then these parts converge to x. So everything together, yjn will converge to x. Okay, so yjn converge to x, sjn also converge to x. So by the continuity of f, what do we have? We have fxjn converge to fx, and also fyjn converge to fx. Okay, so this two subsequence converges to fx, but what do we have just now? We have fyjn minus fxjn greater or equals to epsilon for all n, which is a contradiction. This is from where? This part is from where? From the non-uniform continuity. Okay. Because I just apply, because it is true for all x, Sn and Yn, right? I just applied it to subsequence. Okay, but just now we proved that this subsequence have to converge because the limit point in the domain converge. By continuity, also need to converge. But non-uniform continuity tells you doesn't converge. So contradiction. Okay or not? A question? A question? 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 So this part is from continuity, and then this part is from non-uniform continuity. Okay. You see, if these two converge, how can you say that they always have a gap between them? Should be no gap, right? But there's always a gap. For every n, it's the same gap. We fix an epsilon here. Okay. So contradiction. Does it make sense? Okay. Okay. So yeah, what time is it? I think we can pause here before we go to monotone continuity. Any question for uniform continuity? I think in the exam, I'll confirm again, I think, but we won't have tests on uniform continuity. We will stop at epsilon delta continuity. Okay, so you just need to revise until that part. And then everything behind we will put to the final. But I will put out an official announcement later. Okay, then we will take it. Okay, so let's take a break until what time? 2:03. Okay, 2:03. Hello, testing. Okay. So we quickly run through this monotone function continuity. We won't prove much. Proof will be included in the lecture notes. At first, I thought I want to put this into assignment, but there's no assignment already. So we just quickly discuss this. There's some very important point I want to point out from this part here. So let's do it. So first place you see monotone is where? Monotone sequence. Okay, what is monotone sequence? Monotone sequence is what? A sequence is a monotone if it is non-decreasing or non-increasing. Okay, so here we also can define this kind of notion here. So we can define a function to be monotonely increasing. So in this case here, it is non-decreasing. Okay, non-decreasing. So if what? Actually, last time we briefly see these things already. Right? Not monotonely increasing or non-decreasing. If what? If FV greater or equal to FU for all point. So here is df domain of f for all point uv in f such that v greater than u or u greater than v. If I want more increasing or non-decreasing, u have to greater than v or v have to greater than u. V greater than u. Okay, so all the point behind the f value is larger. Okay, so similarly you can define monotonically decreasing. Okay, or we call it non-increasing. Okay. Okay, so then definition, a function is called monotone if it is either non-decreasing or non-increasing. Okay. Okay. So yeah. So this is, you see, this definition is quite similar to monotone sequence. Okay, but now we look at function. So we look at the f value. Okay, we look at the f values. So there's one theorem that I won't prove. It's very constructive. If you have time, I suggest you to read. Okay, you can see the construction. But what's the main point here? So the main point here is, so there's a theorem here. So suppose f is monotone. So monotone function, how can you imagine it? How can you imagine it? It's like a staircase, right? Staircase. So maybe you maintain and then go down, maintain, go down, or you go out, maintain, go out, maintain, go out, maintain like that. Okay. So if your function is monotone, if fd is an interval, then the function is continuous. Hey, this theorem is very special. How special it is? You just need to check what's your image. Then you will know the continuity. Continuity is what? For all epsilon, you need to exist a delta such that for every point within the delta, you have fx minus fy less than epsilon. Wow, whole thing happens when you have the image of D to be an interval for monotone function. Okay or not? Okay. Okay. So it's quite a very strong result. So the proof is also quite long, okay, quite constructive. Okay, you need to imagine how I gonna find this delta. How I gonna find this delta with the epsilon? I just tell you that image is a interval. Okay or not? But of course, this function is special, not any function. No? This function has to be monotone. Okay, have to be monotone. Okay, this is very special. So this proof left to read. Okay, no need to exercise. You don't need to exercise. This is quite hard. You just read it, understand it. Okay, you don't need to exercise this proof. Quite involved, I would say. And what else? So then the corollary is corollary. So when I put this corollary, meaning you no need to know about the proof, just use the result of the theorem, you can deduce it. So what's this corollary? Let I be an interval, and suppose f I to r is monotone, or monotone, then what? Then f is continuous if and only if fi is an interval. Okay, if and only if. So from the theorem above, which direction is given already? From the right to left, correct or not? If the image is interval, then f is continuous. This is from the theorem above, correct? But the other direction, why is it the other direction is true? If f is continuous, why the image have to be an interval? Sorry? You can use contradiction, but there's one theorem you can use here. Interval means what? Everything's in the middle you can reach. What's the theorem can do that? You can reach the middle thing. Yes, intermediate value theorems. Correct or not? Intermediate, what does intermediate value theorem says? If you pick the endpoint, the interval endpoint A and B, everything in the FA and FB, there's some C such that FC is in the middle of FA and FB. So you can fill out the interval using the image of a continuous function. So that direction, you just need to use a continuous function. You don't need to use monotone. Okay or not? Okay, from the left to right, no need monotone. You just need continuity. But from the right to left, you need monotone. Okay, monotonicity. From the theorem above, suppose f is monotone, fd is interval, then f is continuous. Okay or not? Does it make sense? Question? Got question? Yes. Cannot lo. Wait, what? Can what? Can what? Cannot what? Can what? If f is not monotone, can what? No. Give counter example. Give counter example. Can we work out a counter example? If FD is an interval, but F is not continuous. Can we work out the interval, a counter example on the spot? Can we work out an example on the spot or not? Which one? Wait. You mean like this? Let me think. Hey, true. Bagus, bagus, bagus. So what is FD here? FD here is from where to where? 0 to 1. Yes. Last time we put 1, right? Yeah, 1. So 0 to 1. But it's not continuous at x equal to half. Okay. Okay, let me label it. Otherwise, we are like 空口说白话 like that. Okay, let's do it. So here is like half, right? And then here is 1. So how is this defined? Fx equals to x, right? If x is in between 0 and half. So let me put it here. X, if x is in 0 and half, but here we put x minus half. If x is in half to 1. No more space. Make it smaller. Sorry, half to 1. So I mean, what do we do here? We actually throw out the left one and then we keep the right one. Okay, like this. Is it correct? Correct or not? Not 1, huh? It's just half. Just half. Okay, so this top here is half. Correct or not? Let's see. I think should be correct. Okay. Got question? So here, the f of interval from 0 to 1 is equals to the interval from 0 to half. Okay, but f is not continuous. Yes, you are right. Yeah, very good. Okay, so you should imagine that if f is monotone, this kind of thing cannot happen. So you see, here not monotone, right? You go out, suddenly drop down. If you want to go out, you just can keep going out only. If you want to go down, you can just keep going down only. Okay, you cannot suddenly jump to other place. Okay, makes sense, huh? So the proof is quite involved, so you can just read if you got time. If no time, never mind. I won't test you on this kind of thing. But I want you to know this result. Okay, yeah, so one more important, very important, this one very important, very important. So just now we talked about monotone, right? Now I want strictly monotone. Okay, so strictly monotone means what? So the function, sometimes I just say strictly decreasing or decreasing because we already have non-decreasing, right? So we could say strictly decreasing or just decreasing. For, when do we say this? Okay, we say this if FV less than FU for all UV in D such that V greater than U or U greater than V. If I want decreasing. V greater than U because we want the points behind have a lower F value. Okay. So yeah. Okay, so another definition is, so similarly you can define, so similarly define strictly increasing or simply increasing. Okay, remember last time we stuck very long when defining the subsequence using increasing function. So this is it. So a function is strictly increasing or decreasing. That is either strictly, okay, don't put strictly, just use increasing or decreasing. Is said to be strictly monotone. Okay, said to be strictly. Have you come across any increasing function or decreasing function or not? Can you recall any increasing or decreasing function you know that you learned before? What function are increasing or decreasing? 1 over x. 1 over x looks like what? Something like this, right? Okay, where is increasing, where decreasing? Both got happening, right? So if you restrict your domain from 0 to infinity, then this part is decreasing. Or both is decreasing, huh? If you restrict to both cases. Let me think. Yes. Yes, both of them are decreasing. Yeah. Hey, wait, let me think. Okay, so for this part here, so let me write down. So for f equals to 1 over x on interval from 0 to infinity is decreasing. Okay, how about fx equals to 1 over x on the interval from negative infinity to what? To 0. Decreasing or increasing? Decreasing or increasing? Also decreasing. Okay, also decreasing. Yes, decreasing. Okay, but you cannot put them to study together. You can split them. Another thing, what thing? What thing is increasing? S cube, S cube also increasing, right? S cube. X cube. So for example, S cube, fx equal to x cube is increasing. So last time, how do you show these things increasing? You check the derivative, right? Always positive. Is it true? Always positive. Okay. So how do you check increasing here? You need to check, for example, so check x cube minus y cube is greater than 0 if x minus y is greater or less than. Greater than 0. Okay. So you need to prove this, okay, without what? Without derivative. Can prove or not? This is a bit like the the exercise we did in the real number system, right? Okay, if I tell you x minus y greater than 0, is it true that x cube minus y cube greater than 0? You need to prove. Not too hard, right? You can rewrite x cube minus y cube to be what? X minus y times, I think if I'm not wrong, s squared plus xy plus y squared. Okay, so this part is already positive. So you need to explain why x squared plus y, when x squared plus xy plus y squared is positive. Okay. If both positive or both negative, that term always positive. But let's say one is positive, one is negative, then what happened? Okay, so you need to show that, they are different, still positive, then positive. Make sense or not? Okay, so you need to show for all cases. So show for all cases, this is positive. Show for all cases that it is positive. Because we already know that x minus y is positive. Okay? Can understand what I say? Understand or not? Okay, make sure you understand what I say before you go and execute. When I ask understand, I didn't ask you whether you can do it or not. I'm asking you, do you know what to do or not? Okay, this is very two different things. You need to know what to do first before figuring out how to do. Okay, but a lot of people, they don't ask what to do one. Tell me how to do, tell me how to do, tell me how to do. Okay, I just want to know how to do. And then that person almost always don't know what he is or she is doing one. He just do without knowing what he's doing. Okay, so very important. What to do first, and then figure out how to do. Okay, what come first before how? Okay. This is how you understand pure max. Okay. Let's go on. Let's go on. Okay. I haven't reached the very important part. This is the very important part. So you can see from here. Can you see from here? If it is strictly increasing, right? What can you see here? What can you see here is every domain point is attached to one. It's attached to one what? One point in the core domain. Is it true? True or not? Let's say if you have 2 points reach to the same point, meaning what? This function is not strictly monotone anymore. Correct or not? So if it is strictly monotone, 1 point in the domain must reach to 1 point in the core domain, okay, or in the range. So what does this mean? This means that these functions are one-to-one, which is what we say to be one-to-one. So let me phrase it here. So definition, function f d from R. So this is the domain of f to R is one-to-one if for every point in the image that exists exactly 1 point x in df such that fx equals to y. There's a big confusion here, huh? Confused or not, huh? Y in fd, x in df. You know what is fd and df? Fd is what? Not just core domain, this is the range I can reach by f. The core domain is R. Okay, so I can reach by f, so fd. So everything in the domain apply f. So I mean to be precise here, I should have write fdf. Okay, because df is what? df is the domain of f. Okay. Yeah, so there exists exactly one. So you can show this is equivalent to this definition here. It's a very good exercise to show that this is a equivalent definition of FDF to R is one-to-one if F U equals to FV implies what? U equals to V. Okay. Can you see equivalence here? Every Y, you have one X. So let's say if you have two Y's that are equals, Y1 equals to Y2, then it must come from the same X. Okay, U must equals to V. Okay, show equivalence between these two. Okay. A more useful one would be the second one. Okay. Yeah. Okay. Okay. So what's the relation between strictly monotone and one-to-one here? What's the relation here? If you are so let me put here. So proposition, a strictly monotone function is one-to-one. Okay, try and prove this exercise. Okay, so this is an exercise you should do. I will do it as well, but let's do it. Does it make sense? Does it make sense? Okay, and what else? What kind of property? So since it is one-to-one, right? So it is one-to-one towards its image. So for this one-to-one part, we can construct the inverse. Okay, we can construct inverse. How to construct inverse? Inverse means what? Inverse of this function. So let me put here. So given f from D to R strictly monotone, we can construct inverse from where? Okay, not for OR. I don't construct for OR. I just construct everything from the domain. Okay, back to R somewhere else. Okay, back to R. Okay, so how to construct this? What do I do here? What do I do here? How do we construct this F inverse? Yeah, how do I construct here? So for every Y here, where do I send this to? Huh? X. So what is X here? Such that X is such that what? Such that Fx is equal to Y. Why? Why I do this choice? Why can I do this? Strictly monotone function is 1-to-1. 1-to-1 says what? Every Y have a unique S. So if I do this map here, this map will be well defined because one Y will only give to one X. So I define a function. Okay, so yeah, so I define a function here. Does it make sense? Okay, no. So that's why I need the 1-to-1 because 1-to-1 says every point in the range, I only have one pre-image. Are you guys familiar with the language of pre-image or not? Okay, pre-image. This one image, this one pre-image. Correct? Okay, yeah, pre-image. Only one pre-image. Okay, so if I define like this, Y sent to X, for every Y, there's one unique X. So this is what? This is a function. Function says what? One input only can have one output, cannot have more than one output. Otherwise, I don't know how to send the input. Correct or not? Okay, one input only can send to one output. So this is the uniqueness that give you. Uniqueness says for every point in the image, there's only one output. One input. Okay. So the input here become the output of the inverse. Okay or not? Then you can check. What can you check? You can check that F inverse F is identity. Okay. And then F inverse is also identity. Okay, you can check that. You should recall this is a bit similar to the abstract algebra you learn. This inverse function. Okay, so this is an inverse for the function. Okay, inverse function composed with f composed with inverse function is identity function. Okay, you can check it here. Okay, so this is a particular case of a group element. Okay, not? Yeah. So so invertible function form a group under composition. Okay. Form a group or not? Okay, make sure you have the right codomain and domain, then you can talk about a group. Okay. All right. So let's see. Do we finish here? Okay, I think we can finish here. So I mean finish for this part here. So what? Okay, so from these, right, you can deduce that all these rational function are all continuous. Okay, so for example, so you can deduce here proposition. You can deduce that fx equals to x to the power r for x greater than equal to r. And then what is this r? This r is a rational number. Okay, you can prove that this kind of function is continuous. Okay. Does it make sense? So for example, you can consider fx equals to half x to the power half, right? Or fx equals to x to the power 1/3, like that. Okay, these functions are continuous. Okay, so far what kind of function we've seen is continuous? I mean, not seen, but proven. All the polynomial functions, okay, because we prove the addition of continuous function is continuous, and then scalar multiplication, and then product, and then quotient, okay, are continuous. And then composition of continuous function are continuous. And then now we can deduce also rational power of x also continuous. But I think we still have important function that we haven't proved is continuous. It's like trigo function. Okay, maybe later when we have a chance to introduce trigo function, and then maybe we can comment about their continuity. But for now, if you want to use that they are continuous, you can use it. Okay, but let's see if we have a chance to see why they are continuous later. Okay. And also, what kind of function you guys seen? Logarithm, exponential. So all those will require proof why they are continuous. Okay. Yeah, I'm not sure we have chance to do it or not, but if there's a time to come, then we will do it. All right. Finally, we want to leave continuity already. So any question about continuity? We still have like 13 minutes to do some derivative. Any question on continuity? Even sequences or supremum, infimum, everything. Anything about those? So finally, we want to leave the basic already. We want to go into Newton's world or Leibniz world. Okay, we're gonna do 19th century max calculus. Any question before we go into derivative? Any idea that you think of? You think not sure how to do it? About this, how to find epsilon, delta, or epsilon, or some n. Like when you do your assignment or tutorial, anything come out from your mind or not? Does anything come out from your mind? Anything come out from your mind? When I ask you to play around with the interval, open interval, right? The epsilon, anything come out from your mind? Yeah, very quite important because we need some new ideas. Yeah, we need new ideas. Okay, if not, I haven't go yet. We continue with derivative. So let's do derivative. So let's get us some idea on derivative. So what's derivative? What's derivative? What's the first thing you learn in your high school about derivative? Finding gradient. What gradient you find last time? Of a straight line, right? Of a straight line. For given a straight line, how do you find the gradient? So let's say I find this one. Let's say this line is what do we call it? Y equals to ms, right? Plus c, okay, because I intercept 0, so throw away c. So what's the gradient here? You say that the gradient is m, but how to show that the gradient is m? Y over x. So what are you doing here actually? What is y over x? What is y over x? Hey, put here. So why you said that the gradient equals to y over x equals to m? What are you doing here? Huh? So y x is like this, right? Y and x. So you are referring y and x to the origin 0 here. Okay. So you are what do you referring to? You are referring to the difference between y and 0 and the difference between x and 0 here. It's the ratio, in other words. Okay, it's the ratio of the change in y and the change in x. Correct or not? Okay. Or let's say we fix some points here, right? So to be a bit more precise in our language, so we can write this as fx equal to mx, right? To be a bit precise for our language here. So let's say we pick other 2 points. What do I mean by other 2 points? Let's say we pick, how about we pick 1 and 3? Okay, let's pick 1 and 3. x1 equals to 1, x2 equals to 3. What is fx1 and fx2? What is fx1 and fx2? Is 1 times m, right? So m, and then 3 times m, 3m. Okay, so we got here is m, here is 3m. Okay, so we can look at the ratio again. What's the ratio we want to look at? fx1 minus fx2 over 1 minus 3. Correct or not? x1 minus x2. What is this number here? M minus 3m and then 1 minus 3, which is what? Which is again m. Wow. We change 2 points. We look at the ratio of y and ratio of x. Still the same, or? Huh? Still the same, eh? How come? So what are we looking at? So actually, the gradient of this curve here is represented by the curve itself, this line itself, this straight line here. So at every point, the gradient is just m. Okay, represented by this curve. Does it make sense? Okay. So from this curve, right? How do we study a random curve? Okay, so how do we study a random curve? So for example, now my graph a bit weird already. So maybe my graph may look like this. Okay. So I want to ask, what's the gradient here? The gradient. Okay, so what can I do? Okay, so what can I do here? So what can I do? What can I do here? Where is the ratio I want to look at here? What's the ratio we can look at here? What's 0? Sorry. So maybe put this point as P. So what's the ratio we can look at here? Okay, just now everywhere is the same, right? But here, how? how to find a gradient here at this point? Zero over P. You mean FP? What do you mean by 0 over P? 0 over P. Oh, FP minus FP over P minus P. That is 0 divided by 0. What can we do? But we can do similar things. What do we mean by similar things? You can consider nearby points. Okay, you can consider nearby points. Maybe we call this x1. Then this one is fx1. Okay. And then what's the similar thing we can do here? We can compute the ratio between fp and fx1 over p minus x1. Okay. And then here we can get some ratio. So let me put it here. xf1 minus fp over x1 minus fp. Okay, we can get some ratio here. And then what? What is this? This is just the secant that join these two, right? I mean the gradient for this line here. Okay, what else? I can consider more points, right? Like that. Correct or not? Nearby points. And then what? And then we can keep doing it for all the nearby image point. Okay. Then once you do until this stage, what happened? It's like what? Like what? Jack say, no? FP minus FP over P minus P. Seriously. But there's a special thing happens here. If you take this limit, limit x to p of so we keep doing it, right? So we keep doing it. So fx minus fp over x minus p. At p, it is what Jack say, fp minus fp over x minus p. But this term here will come out something different for different example. Okay, let's try one example. You don't believe me, is it? I try example. So let's try one example. Let's try example on fx equals to x squared. Okay, let's say we fix this p. Where do we want to find this p? You want to pick a p or not? P0, p equals 0. Want to fix p equals 0? Okay, let's find this value at p equals 0. Okay, let's give you an example to show that this term here is non-trivial. So I'll find this value for this function fx equals to x squared at p equals 0. So what happened here? So what is fx equals minus fp in this case over x minus p? What is the middle term here? We have x squared, right? We have x squared minus fp leh. fp is just 0. X over 0. Okay. And then what do I get here? So p is 0. What do I get here? Limit of x going to 0. X is 0. If fp minus fp over p minus p, this thing shouldn't be defined. But here says that it is 0. Okay, let's change another point. Change another point. Okay, let's change different point. What if P equals to, let's say 2? What happens when P equals to 2? So I get x squared minus 2 squared is 4 over x minus 2. What is this? This one equal to 2. And then this one go to 2. Then what is this? This is a limit of x plus 2, which is 4. At 2 is the gradient is 4. Okay. Change again. Keep changing. Okay. And then what if limit going to -2? So still we get x squared minus 4. At the bottom we get x plus 2. In this case here, this limit is what? -4. Does this match up with the gradient on x squared or not? So it says that at this point, so at the 0 point, the secant is 0. But at the point of 2, the gradient of this secant is 4. But at -2, this secant, the gradient is -4. Correct? Okay. So you see, once you take the limit, it's not the exact point on the function. So that's why when we study continuity and limit point, we split the two concepts. This secant function here, this secant function here, the limit from S to P is more interesting than evaluate this function at P. Understand? Understand or not? If you evaluate at P, undefined. But if you just look at the limit, it will be something useful. Okay. So to this end, 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 what do we do? So to this end, we will define that I be an interval containing x naught. Then we will define the function fi to r is differentiable. Okay. Previously we defined what is continuous. Now I define is differentiable as s naught if you look at the limit of the sequence, it exists. Okay. If it exists, okay, if you can find this limit, then that means this function is differentiable. That's all. Okay, this is called a differentiable function at S naught. Okay or not? So in this case, we did not, what time is it? Oh, 5 already. Okay, quickly. So we denote this function. So we denote this limit. We denote this limit as f prime s naught. Okay. Does it make sense? Okay. Let's see. Should we pause here? Maybe let's pause here and we will continue next time. Okay. So whenever we want to talk about differentiability now, we will talk about the limit of the. This is what we call a I think we also mentioned in calculus 2, this thing is a secant function. Okay. Because you look at the ratio of the difference of y and difference of x. This is a secant. Okay. We will start from here again next time. Okay, I want to give you an idea. So whenever we talk about derivative, it is the limit of the secant function here. Okay. Okay, I think we need to leave here quickly over time.